This is a related rate example. I call this a cone example, or where something is flowing out of a certain type of object. So we have a liquid that's being cleared of sediment by pouring it through a conical filter that is 16 centimeters high and has a radius of 4 centimeters at the top. Suppose that all the liquid flows out from the cone at a constant rate of 2 centimeters cubed per minute. At what rate is the depth of the liquid changing at the instant when the level is 8 centimeters deep? Okay, when we're talking about depth, think of depth. You might want to think of depth as the height. That's an H. As the height. Okay, so let's talk about what we have. We have a cone, like a funnel, and it's being cleared of sediment. And this cone is 16 by 4, and I have stuff flowing out of it at a rate of 2 centimeters cubed per minute. Now, what is that a measurement of? That's how our volume is changing every minute. Okay, so I know dV dt is 2 centimeters cubed per minute. Okay, let's look at what else we know. What else do we know? Okay, I'm looking for how the depth of the liquid, or the height, I'm looking for dH dt when the level, when h is equal to 8 centimeters. So our equation has to involve volume since I'm given dV dt. So volume of a cone is 1/3 pi r squared h. Now, if I were to take a derivative of this, we would have a product rule because we have two variables, r squared and h, and we would have dr dt. They don't tell us anything about how r is changing. So we need to essentially get rid of this r squared. So we need to write a relationship between r and h. So at any point here, at any point h, when our liquid is moving through versus r, we have similar triangles. So 16 is to h as 4 is to r. Or I need to get rid of r, so r is going to equal h over 4. So I need to substitute this back into my volume equation. And then simplify. When I simplify that, I get pi over 48 h cubed. Okay, so now I need to find dV dt. When I find dV dt, I bring the exponent down and I simplify. I take the derivative of h, and then since I'm taking the derivative with respect to time, it's dH dt. Okay, so then I plug in. Okay, when I'm plugging in here, dV dt, something that you need to keep in mind that I didn't think about till now when I was looking at my notes, the volume is changing. Volume is flowing out of our cone. That means it's changing negatively because it's decreasing. So dV dt is actually negative 2. We know our height is 8 centimeters, and we know h, dH dt is what I'm looking for. Okay, so when I go through and I solve this, I get negative 1 over 2 pi dH dt, and I should probably put units on there. So negative 1 over 2 pi. We are flowing at centimeters per minute. And you do need that negative, because if you look at the question, it says, at what rate is the depth of the liquid changing? If it were to say, at what rate is the depth of the liquid decreasing, the negative, you wouldn't need the negative. But you need the negative because the depth is going down because our material is flowing out of our cone.